Today's episode is called The Net That Keeps the Relations, Object-Centric Petri Net Discovery for Multi-Agent Systems. So last episode, we were speaking how object-centric event logs keep every relation. And the rule that we set is that we would have to flatten last. But a log isn't a picture. So you still need a model, and you need to see what flows in what order. Of course, the idea here is to be able to replay against it, to have conformance. So the tempting shortcut here is to flatten, but of course you'd have, as usual, divergence and convergence problems. But we need a model that speaks the many-to-many relationship natively, of course. One event here needs to touch many objects, and it has to be expressible in the model itself, with no case notion ever. That model is the object-centric Petri net. So you have one net. This is our Petri net. You have several object types and a single firing that can move a whole set of tokens at once. So the rest of this episode, we're going to be talking about object-centric Petri nets. So in previous episodes, we have discussed what is a Petri net. So here you have the circles here is what we call places. And this is a transition. The idea is that when you fire this transition, you're going to move this token from here to here. Simple enough. Now, a normal arc moves only one token. You could, of course, and this is an idea that we proposed already, weigh the following transition, this arc, put it at 3. But that reaches a problem. Is that, let's say we need a count that is varying. So one run delegates 3, the next run is delegating 5. A fixed weight can't say a set whose size changes every event. So it will always be 3, which is blocking us here. So a classic called Petri net then hits a wall. This is where agent work really lives. So the object Petri net is basically a labeled Petri net that has 2 additions. First is the typed places. So every place, every circle that we have seen already, has only one type of tokens. And that type is an object. Also, we have a function that maps every place to the type of token. So that's first. The second is that we have variable arcs. What does that mean? Let's look at this. So this is the normal one. So it's single line and it binds one object. Here with a variable arc, we have double lines. This means it's binding a set. Now let's go next. So let's look at the definition here. So the formal term is variable arcs. The paper from 2020 discovering object-centric Petri nets also says multi-set arcs. So the idea here is that you're going to be able to transport many of these tokens through the firing of this transition. So it's not really transport. So these tokens will be consumed. Many of these tokens will be consumed, and then either one or many tokens will be produced in another place. Of course, this place has its own type. So the tokens produced here will be the type of this place. So let's look at this example. So here we have a normal arc between the place. So this place only takes supervisor tokens. And then we have a normal arc and then this transition. Let's say we fire this. What will happen? When we fire, here, this arc is variable. It can be 3, it can be 4, it can be 7. But in this instance, let's say supervisor, we have an E2O table, event to object table. We look it up. We say supervisor number 42, for example, number 42. And we see how many number 42 is mapping on the object side. In this instance, it's 3. So we have 3 tokens here. And then, like next time, let's say supervisor number 5, and then that maps to 2 tokens. So when we fire this, it would produce 2 tokens actually. Each of these tokens are related to an ID of an object. As you can see here, we fire 1, we produce 3. That's the single step. Now, from the formal side is that we have here the cardinality, we have the binding B that represents how many objects of each type we have here, and then the marking here is the previous marking. So this is the new marking, and it's the previous marking, the tokens that were consumed plus the ones that were produced. One rule for well-formedness here is that for a transition, an object type is connected by variable arcs or by normal arcs, never both. So for a transition, an object type is connected by variable arcs or by normal arcs. You need to make a choice. You cannot have both arcs. So because different types with different arc kinds is exactly the point here. So many-to-many is now a first-class element of the model, so not something you flatten away. And now we don't need to flatten, of course. So let's look here. Let's take this example. A transition can touch more than one object type. And let's say here, delegate, you have arcs from task, from supervisor, from message, everything is clear. And you wanna give it a name. So here, the literature gave it a name, and it gave it the name of shared activity, interaction, transition over multiple types. This is from a paper from Van der Ras and Bertie. And you might be tempted to call synchronization, but that's a very different thing. This is something we will talk about in other in other papers and in other videos. Synchronization is stronger than what this entails. So for now, forget about synchronization, just call it interaction. We will come back to this later on. And one thing that's nice is that here we are keeping the same type of interactions that flattening could destroy with this structure. So how does this work for PM4Pi? How to take from OCEL and go to OCPN? The idea is very simple. You have 4 steps. You could actually do it with PM4Pi with any general miner. First of all, you're gonna create a flattening that's gonna work per object type. So that's the first step. Second, you're gonna create a Petri net that is accepting Petri net for each type. Here we're gonna go, the inductive miner is used by default, but any miner could work here, heuristic or whatever. 3, you merge these nets by fusing transitions that share an activity label. So you have different nets and they have different activities, and then here the idea is that you fuse the transitions that share an activity label. So simple enough. And that fusion is where shared activity becomes one multi-type transition, just as we have seen the last slide. So one thing is that the object-centric model is basically the per-type view glued at the shared label transitions. So it's like you're taking multiple nets and you're trying to fuse them together through their transitions. That's the idea of that. But here you have limitations. First of all, the flattening that you're gonna do here is problematic because you're gonna be creating convergence and divergence artifacts, and they can sneak in before the merge. And naive merging, which is here, can produce an unsound model for certain looping interactions between objects. So that's the second issue. So you can't do it naively. Of course, there is research how to do it in a non-naive way, but these are the 2 honest limitations we have. Now, let's look a little bit about PM4Pi code. So frankly, I just realized that the more plot code is improving, the less it is useful to explain to you what each of these functions mean, but you just can read them and they will give you an idea about what each of these do. So, and here the discover Object-Centric Petri net will give you basically a dictionary. Here you have you have an agent and you have a task. And one thing to remember, the contrast that matters is that the object-centric DFG that here we are producing is just a frequency annotated directly follows picture. So it's just something we use as a reading aid. It's not execution semantics. Only OCPN has token binding semantics, and only it can be replayable and conformance checkable. So that's one thing. DFGs are not conformance checkable, of course. This is something we have seen in a previous video. And one thing to also say is that object-centric conformance is really young as a field. Alignments exist, but they are very recent. You have the paper from 2023. They are harder too, and each variable arc transition must first be expanded into finitely many non-variable ones. That's a very big issue. So every real discovered OCPN gets brutally complex. So the field is still really new. We still have a lot of research to do to make it more industry adapted, and especially that process mining is known for accepting a lot of data, and here it's the research needs to catch up to the needs of the industry. Now, to give you a full perspective and a recap, first of all, multi-agent systems fail at the interactions level at 32% of failures. That's for the failure modes. So the interactions between agents are generally a huge source of failures for these multi-agent systems. The object-centric Petri nets make these interactions first-class transitions. So it's basically the structure that you must see. And here it would show you the exact places where the system is breaking, because you have your conformance, you would know when these interactions are not working. And the problem is that there is no published work that applies object-centric Petri net discovery to multi-agent LLM traces yet. So this series, we are talking about it. Hopefully, if I get enough resources, I would be able to research about this, but yeah, I'm too broke for that shit. And one thing that happened is that the empirical anchor, so this is a paper that we have spoken about in previous episodes, is that we had 290 runs of 3 agents coming from Core AI. A single case miner already caught a real, so that's for the single case miner. The project, so this is the bug. The project invoked math tools. It was never granted, so it didn't have the grant to get access to the math tools. So here, single case was enough at 3 agents, and we had 1 input, but object-centric Petri nets is what is gonna be needed to scale to real interaction structure. These are the different chapters and the different ideas from our video. If you have one that is not clear, please go back and view them again. And finally, for last word, keep the relations, and now the model keeps them too. Thank you. If you like my content, please like and subscribe, and follow me on LinkedIn.